our second talk this morning is David Favero, who is going to tell us about homotopy path algebras.
Okay, thank you, Tony, and for the introduction, and thank you to the organizers for inviting me to speak. Unfortunately, it had to be virtual. I'm actually putting my house up for sale tomorrow. So yeah, that's right, that I'm going to be talking about homotopy path algebras. And this is some kind of class of algebras that I want to give an introduction to and some kind of sales pitch on. This is joint work with Jesse Huang. So here's the structure of my talk today. I'm going to start with some kind of introduction to homotopy path algebras. What are those? I'm going to talk about HPAs and their relation to constructible sheaves and entrance paths. Then I'm going to talk about minimal resolutions of an HPA as an algebra. I'm going to talk about minimal resolutions as that algebra as a bimodule. And finally, I'll talk about the connection to homological mirror symmetry, especially toric varieties, following closely the ideas of Bondal from late 1990s. Okay, so we're starting with the introduction to these homotopy path algebras. All right, so I'm going to start with a quiver Q, which I'll think of as a directed graph with possibly multiple directed edges. And we consider an embedding. Instead of just thinking of Q, I want to think of Q as embedded in a topological space X. So my first definition of a homotopy path algebra will just be the path algebra of the quiver, KQ, modulo the ideal of relations given by path homotopy. So it's the algebra of K linear combinations of directed paths in Q up to homotopy in X. So this is the class of algebras that I'm going to spend the whole day talking about. So I'm going to give you an alternative definition now as well. So I'll work over any commutative base rank. Okay. If Q, well, first of all, I'm going to detail that definition I just gave. So if Q is sitting inside X, this isn't my alternative definition yet. Then I'm just specifically saying that I take the ideal P minus Q, where P and Q are paths in Q up to path homotopy in X. So I take the ideal generated that, and then this homotopy path algebra AX is just KQX, well, KQ, maybe there's no X, yeah, mod IX. Okay. So very basic example. If I take this square quiver and think of it on a square or on a disk, then A is just KQ, the path algebra of this quiver, mod the relation AB minus CD, because I glued a disk that made those two paths homotopic. Okay, so that leads to my second definition. So a homotopy path algebra can just be regarded as a quotient KQ mod I, where I has a specific form. So I has to be generated by P minus Q. P and Q have to have the same head and tail, right? So P and Q have the same starting and ending point. And if X times P minus Q is an I, this implies P minus Q is an I. Because of course, if X times P minus Q are path homotopic, then P and Q are path homotopic. X times P is path homotopic to X times Q. All right, so this is the only condition on this kind of idea. And of course, my two definitions are equivalent. So given, starting from definition 2, if I'm given this kind of path homotopy algebra, I just need to construct a topological space. This is easy to do. So for each P minus Q in I, just glue a disk with boundary PQ inverse. And okay, so you got some kind of two-dimensional CW complex that obviously has this quantity, but maybe that's not such a great answer. So maybe a question is there a more canonical choice? Of course, this is a leading question. So that was just kind of the two skeleton of X. What's the full answer for X? Well, let's go back to this, this algebra. From this algebra, I can construct a category, which I'll call CA. The objects are the vertices of A, of Q. And the morphisms are paths in A. Then I define XA to be the classifying space of this category. And naturally, the quiver, the original quiver, embeds into this XA. So let me expand on just what this is in an example. So XA is the classifying space of this category. That means this is a simplicial complex where zero simplices are objects, in this case vertices. One simplices are morphisms, in this case paths. Two simplices are compositions, in this case looks like this. So if I took this example, I almost get this thing where I fill this in. The simplicial complex structure is slightly different. So I have my X, my Y, my A, and my B. And now I have this one intermediate path, which is XY, which is the same as AB. And so now we fill this in with these two cells. Okay, so we get a disk in this case. So let's do a more complicated example. I'm sure people are in the know of what this actually is, but I'll pretend that we don't. know that this is the balancing quiver for P2. So I'm going to look at this quiver. And I'm going to add these relations. So x times y is y times x times z is z times x, etc. Okay, so now if I look at this classifying space of these algebras, here I have these three objects. Those correspond to three vertices. And this is one vertex that I've just drawn in the universal cover. Okay, I have my three arrows. Those correspond to these three arrows, x, y, and z. And then I have three arrows from here to here. And now I have things like the path xy, which is equal to the path yx. This locally looked like the same thing on the on the previous page. So I just get this disk from this relation. And for example, this disk here, which is here, is the disk from this relation. And the disk from this relation is here. So this is a torus. And I should say it's not quite a torus. It has these three flaps on it. So you have x and x squared. They were difficult to draw in this picture. You know, they're getting glued. There's some kind of triangle kind of getting glued here. Okay. And there's three of those. But certainly this is homotopic to a torus. Two-dimensional torus. Any questions? So also a trivial example. If you take the trivial ideal, then XA is actually always homotopic to the quiver itself. But it's not equal. So for example, take this quiver. You added this XY and this YX, sorry, this YZ, and these two disks, but of course, the deformation retracts to this quiver. Okay, another kind of fun example is that actually XA can be any regular CW complex. So let me explain why. So if I take any regular CW complex, then I can make the cells, I can take the vertices to be the cells of Y. And the arrows are going to be boundary maps. So I'll call it AI is an arrow from the cell E, which is a vertice, to some boundary of that cell. And the ideal is just AI AJ minus AJ AI. Of course, if I take delta I, delta J, I get the same boundary. Okay. So you can think of this as a path from the cell to its boundary. Then this classifying space is just Y. It's actually the barycentric subdivision of Y. Okay. So this XA could be, in principle, any regular CW complex.
David, is it always going to be truncated?
What do you mean?
Are the homotopy groups going to be always trivial above some level?
Well, okay, so you don't have to take a finite quiver, but for the purposes of this talk, I'm going to simplify and say that the quiver is finite.
Does this mean that this universal classifying space that you're defining will be truncated?
Yes. I mean, I mean the truncated classifying space.
Okay.
So now I want to talk about the connection between these homotopy path algebras and constructible sheaves and entrance paths. Some of this is an idea that goes back to Bondal and Ruan. And this is, well, maybe all of this is. Yeah. So first I want to stratify this classifying space. So I want to talk about the tree stratification. So for each vertex in my homotopy path algebra, I want to consider the union. This is inside of, this is a subspace of XA. Okay. And it consists of cells corresponding to concatenation of morphisms, P1, this concatenation of morphisms. Okay, so I've written this as a chain in the poset of paths. So if I start at EV and then I just go outward, that's my definition of KV, is paths starting at V. So cells whose paths started at V. Okay, I'll draw a picture in a moment on the next slide. So I can define a stratification of XA where called with I just take KV and I delete the union W greater than V. Okay, W. Okay. And I'm going to call this the tree stratification of this classifying space. Okay, questions? So I'll draw a picture in a moment, but first I want to state a theorem, and we'll expand on this in a second. So actually, essentially, I'll expand on this too. The stock functor induces an equivalence between constructible sheaves on the classifying space, stratified by this tree stratification, and modules over the homotopy path algebra. And this takes, for example, the constant sheaf on this tree, on this stratum, to the simple A module. Sorry, maybe this was B. B. No. Okay, so that was the tree stratification. We have some other stratifications as well. So now let I be any finite poset, okay? And take some topological space Y stratified by this finite poset. So this is a poset stratification of Y. So I'm going to call it exceptional. If each of the SV is contractible, and if I take SV intersect SW, this actually determines the partial ordering on I. So this is empty if and only if. Sorry, this should be non-empty if and only W. Okay. And then actually you have to take the transitive closure to get the post-set ordering. Let's say this really implies this, and it's equivalent to the so you get a transitive ordering on these strata based on this, and you take the you take the transitive closure of this ordering on these strata. No, that's I. Okay, so I want to do one more kind of stratification. So let Y be a regular CW complex again. Then a stratification of Y is called cellular if it's a coarsening of the CW strata. So that just means that each strata is a union of open cells. Yeah. So given a poset stratified space, I can define entrance paths. The category of entrance paths, oops, some of this was supposed to be erased. Maybe I'll hide it, yeah. So the objects in the entrance path category are just points. And morphisms are paths, satisfying the fact that this path is passing, as it moves in an ordered fashion along this poset order along these strata. So if it goes from one strata to the other, it always passes to a lower stratum in terms of this ordering. So that's codified here. If I take the pre-image of the stratification, I get an interval of each strata. I get an interval, and that interval, the maximum of that interval is less than the maximum of the next interval, or an internal piece in that interval is less than the next piece. If V is less than W. So I'm just descending in terms of the stratification. I'm descending in the post-set ordering. Can I take those paths up to homotopy? So this is kind of like the fundamental groupoid, except that now it's directed by this post-set stratification. Okay, so now I can take the homotopy path algebra. I can to this S in this stratification. I can also associate a homotopy path algebra. Vertices are just going to can be thought of as the strata, or they're just indexed by I. And arrows are just going to be entrance paths. I'll have a picture in a moment. From XV to XW, meaning where these are some chosen base points in each strata. So just choose a base point in each strata, and you can make this. Now I assumed these strata were contractible, so it's going to be independent. Well, I will assume these strata are contractible. Okay. So here's an example. This is maybe a familiar stratification of the Taurus. This goes back to Bondal. But let's just think about it as a stratification of the Taurus. So coming out from this stratum, I have 3 entrance paths to this stratum, which I'm thinking of as green. Okay. So I get 3 entrance paths. 1, 2, 3. And three more going in here. And of course, I have the compositions of these paths are also the arrows like this, but they're just given by concatenation. So it's represented by this quiver. And if, for example, I do this, then this, I claim that's the same as doing this, then this, yeah, because they're both this path here. So I get these three relations.
David, what's your poset here?
Yeah, my poset is the set 1, 2, 3. If you want, or 0, 1, 2. Thank you. Is that okay?
Yep.
Yeah. Good question. I did not say. Okay, so theorem. So I want to assume that my stratification is both exceptional and cellular. Okay, so each of these is a union of open CW cells. Each one is contractible, and they're stratified by a poset with this condition on the boundary, giving the poset the poset ordering. Okay, and the theorem is 1, Y is homotopic to the classifying space of this entrance path, homotopy path algebra I just defined. 2, sheaves on Y constructible sheaves with respect to this stratification on Y are the same thing. Are the same thing as sheaves with this tree stratification, constructible sheaves with respect to the tree stratification on this classifying space. And this equivalence is induced by this homotopy. Okay, you can take the stock of a sheaf, and then similar to the fact that representations of the fundamental group give local systems, the stock of such a sheaf gives functors from the entrance path category to, in this case, K modules. K is our commutative base ring. And there's also equivalence here. Everything commutes, induced by this homotopy with functors from the entrance paths on this classifying space with this tree stratification to K mod. And then, like I said, choosing a base point is just giving an equivalence with modules over this homotopy path algebra. And a nice consequence is that this equivalence takes, you can think of this as a generating exceptional collection if you want. It takes K SV to strata to strata, right? So the strata on Y to the strata on the tree strata. So there's somehow these strata on Y are being deformed to these tree strata. All right, so I tried to illustrate this in this example. So I took the torus and we talked about this stratification of the torus by the poset 1, 2, 3, right? Entrance paths gave me this quiver with these commutative relations, xy minus yx, dot, dot, dot. Okay. And on the other hand, we had this picture of the classifying space, which was the same torus, but it had these three guys. So I'm just going to homotop these down, but I actually also collapse this stratum here to this picture. So really on this torus, this is collapsing like this. But it's still a torus. Well, sorry, it's still this space where this stratum here is just the whole space minus this and this, right? And then the next stratum, so these two strata correspond to under homotopy. The next stratum is this, which I told you how it's deforming down, and then a point is still a point. Okay, so that's how we interpolate between this stratification and this tree stratification. All right. A next very natural thing to consider is what's the resolution of the diagonal for these homotopy path algebras. So we didn't get a completely satisfactory answer to this question, but we have some construction, and we know it works with this condition. So I'm going to say a simplicial complex is pure of dimension d if it's a union of d simplices. And it's called shellable. This is the notion I want to introduce. It's called shellable if there exists an ordering of these simplices here. I numbered them, so I'll pretend they're already ordered, such that if I take the kth simplex and I intersect it with the lower simplices, then the intersection has dimension d minus 1. This should say it's pure of dimension d minus 1. So anyway, this is just some kind of standard condition. It's known that this implies Cajole for Stanley-Reisner rings, and I want to say the same thing eventually. So in the context of homotopy path algebra, so let A be a homotopy path algebra. For any path in A, we can consider the interval. So this, I really mean the full subcategory, and I'll have some bad notation here. I'll think of a full subcategory as a set. So I mean the full subcategory of P in A such that P divides Q. So think of this poset. Yeah, this is a poset. So you can talk about if the order complex is shellable. I'm going to say that A is shellable. The order complex of this poset is shellable for all P. Or I allow actually that it's not shellable, that it's just a finite set of points. Okay, so you can kind of forget this condition now. It's just the condition that I need in a moment. Okay, so what do we know about the minimal resolution of A as an AA bimodule? Well, in fact, there's always a natural cellular resolution of A as an AA bimodule, such that the rank of the PI is equal to the number, this is what cellular really means, number of I cells. And cellular, it's kind of functorial map from the open cells of this XA. You can forget about what that means. Okay, so there's always this resolution, but now furthermore, if this HPA is shellable, then it's causal. And in fact, there's a sequence of simplicial collapses from the classifying space of A to something I'll call XA bar. So now the rank of PI min is equal to the number of I cells in XA bar. So in other words, you can get this minimal guy, which is also a cellular resolution of A, and it's actually the minimal resolution of A. So again, if I is 0, this XA bar is nothing more than the quiver back. So here's XA bar, was just the original quiver. The cellular resolution is just the points and the arrows. You don't want, there's, of course, with a quiver is hereditary algebra, you don't want any of these disks. Okay. So back to this example, this is a running example for this talk. If I took this balancing quiver, and implicitly I always mean I have these relations. This was XA, it was this torus with these 3 guys on it. But in fact, the minimal resolution is exactly this torus. So you collapse one of these cells in each disk, so that these are just, you only have 1, 2, 3 2 cells, right? And so it just looks exactly like this CW stratification of the torus. Okay. This is the minimal resolution. Okay, so now I want to tie all this back to toric geometry and mirror symmetry. So homotopy HPA or homotopy path algebras, toric varieties, and mirror symmetry. So let's talk about toric HPAs. These naturally, this is the motivation actually, of course, was that these appear in toric geometry. So if I have L1 through LT are line bundles on a toric stack, then it's always the case that the endomorphism algebra of the sum of the line bundles is HPA. This is not difficult. So I want to specialize a little bit to full strong exceptional collections of line bundles, which were introduced by Bondal-Ruan, which came from the image of the Frobenius map. But I'll simplify the exposition a little bit. So the setup is I start with any smooth projective toric Deligne-Mumford stack. I'm going to actually, but I want to think of it as a GIT quotient. So it's gonna, I'm gonna have this sequence of abelian groups. M goes to Z to the number of rays, goes to the co-kernel or the character group of this G. Okay. So I take some open subset in here and I quotient by G as a stack. Okay, so now I'm going to define a set phi here, which here this map is mu. And this phi is I take mu R of what's called the zonotope. Well, this open zonotope, half open zonotope. So sorry, that's not R, that's whatever the rank of this. So sigma alpha. So I take the image of this kind of this cube, this unit cube, this half open unit cube, and I intersect it with G hat. Okay, so this gives me actually a finite subset in here. Basically, this is a bounded subset. Finite thing here. So I'm going to say that this toric variety or toric stack or DM stack is of Bondal-Ruan type. If O of D such that D is in phi. So I just think of, I have all these characters. I think of the corresponding line bundle on this toric stack. I look at this collection and it's of Bondal-Ruan type if this is a full strong exceptional collection. So Bondal and Ruan in their original report gave a nice class of toric varieties which satisfy this. They just require basically that any curve intersects the toric boundary at most with at most -1. The intersection of any curve with the toric boundary, if you look at the individual pieces, has a -1 and the rest have to be positive. One can be -1. So basically, Bondal commented in that report that, for example, 16 of the 18 toric Fano threefolds all satisfy this property. Okay. So now, if I have a exceptional collection of Bondal-Ruan type, then as before, I get a homotopy path algebra given by the sum over D and phi O of D. And this is going to be called the Bondal-Ruan HPA. So I get this nice HPA. Finally, this strata I've been drawing is the Bondal-Ruan stratification. This stratification of the two torus is an example of a Bondal-Ruan stratification. So I can take my n torus, which I think of as MR by M. And I had this map mu. Mu was a map from I can think of this as the fiber of really MR quotiented by M. Okay. And then I can take this stratum is going to be mu R inverse of 0 intersect 0, 1 to the sigma of 1 plus d. Okay. So Bondal actually just defined this as the level sets of some kind of discrete function to G hat. This is a alternative description. And so then this stratifies the torus. I'm going to call this the Bondal-Ruan stratification. All right, so here's the theorem. If X sigma is a toric variety of Bondal-Ruan type, then 1, this is all a consequence of what I talked about in generality now. So now X, so this stratification is a exceptional cellular stratification. It's not actually hard to show. So in particular, this classifying space is homotopic to a torus. In fact, the path algebra of one of these Bondal-Ruan exceptional collections is shellable. This HPA is shellable, which means that A phi which actually is the endomorphism algebra of the sum over D in phi of the, well, I should probably put pi shriek here, of the push forward to the torus of the polytope associated to D is causal. So the Bondal-Ruan HPA is causal, and the causal dual is just the endomorphism algebra of the strata. This is probably, oh, it doesn't matter because this is compact. And finally, the derived category of the toric variety we know is equivalent by assumption to the derived category of this Homotopy path algebra, which by causal duality is the derived category of the causal dual. On the other hand, we know that this homotopy path algebra is the same thing as the derived category of sheaves with the tree stratification on the classifying space, which we know is homotopic to the derived category of sheaves with the Bondal-Ruan stratification on the torus, which is the FLTZ mirror, same thing as the derived category of sheaves. Maybe the notation is slightly different. You have the FLTZ skeleton here. Sheaves on T. Okay, so this is some version of homological mirror symmetry, is that the derived category of this toric variety is the derived category of sheaves with this skeleton. And then you can pass to some kind of Fukaya category on the cotangent space of this with stops. So I want to make one comment. I'm almost finished now. So this was a separate theorem that I want to give you a non-toric example. So let X be a Gorenstein BHK hypersurface with maximal symmetry. So you can think, for example, of the Fermat hypersurface in some projective space. And more generally, some kind of weighted projective space with some kind of nice class of polynomial. And I want to have a large group action where if I had the Fermat hypersurface, for example, I would take like ZD to the n plus 1 acting on this. So I take that quotient. This is in fact a rational stack. Okay. And there exists a full strong exceptional collection on X such that its endomorphism algebra is an HPA. Okay. So these are rational but non-toric examples. So I end with a conjecture here. This conjecture is really due to Orlov. So really, Orlov's conjecture doesn't have this. So if I have any full exceptional collection on a variety X, and it doesn't have this assumption, so cross these out, then X is rational. This is the conjecture. So if I have a full exceptional collection on a variety, then X is rational. Well, now I want to strengthen this. I want to assume I have a full strong exceptional collection such that the endomorphism algebra is a homotopy path algebra. And I want to see how maybe this works in this case. So I claim there's going to be a torus embedded in this classifying space up to homotopy, and local systems on this torus will correspond to, well, these correspond to pi1 of the torus mapping to maybe, let's say C star. So this corresponds to C star to the n. And so over here, you get these rational points. Okay. But they need not act on the full space because it's only some embedded torus. So this does not have to, you don't have to have a torus action on this side. Okay, that is all. I'm stop there.
Thank you, David. Any questions? I think we'll thank David again. And let him go self discover.
Thank you, Tony. Nice to see you. I wish I was there.